Welcome to our talk, Lego Builder's Journey, Rendering Realistic Lego Bricks in Unity. I'm Mikkel Fredborg from Light Brick Studio. We're a small startup in Copenhagen, Denmark that was created through a spin-out from the Lego Group. Our debut game, Lego Builder's Journey, won Mobile Game of the Year in 2020, and this year we released an extended version of the game for PCs, Nintendo Switch, and Apple Arcade. I work as technical lead, and among other things, I'm responsible for lighting, shading, and rendering, which is very much what this talk is about. For the PC version, we wanted to see how far we could push the realism, and we worked with both NVIDIA and Unity on making that happen. I will give you an insight into how we approach the visual upgrade in the PC version using ray tracing in high-definition render pipeline, and also give you a brief overview of our process in general and generally, and hopefully some ideas and inspiration. Once I'm done, Paul Hodgson, also known as Hodge from NVIDIA, will take over and give some details about the DLSS implementation coming to Unity 2021.2 later this year. But let's start by taking a look at some real Lego bricks so we know what it's all about. Almost everybody knows Lego bricks, and most people have spent countless hours playing with them, so they instinctively know what they look and feel like, which doesn't make the challenge of rendering them any easier. But after all, it's just some pieces of plastic with some tubes on top. That should be easy to render. Well, it's a little more detailed than that. So here's a real Lego brick. It has bevels on all the edges. It has logos on the studs. It has injection points from the molding process, typically on one of the studs, but it can be in other places. They have a lot of interior details. There are tubes that make them snap together nicely. There are insides of the studs, the small extrusions to improve snapping and to make them more stable, and things like ID numbers and molding machine ID and so on are embossed on the inside. They are also translucent, and you can actually see light passing through the thin parts of the bricks. And the different colors of plastic have different diffusion profiles, meaning they let through more or less amounts of light, depending on what color it is. And of course, Lego bricks are super precise. That's why they work. But as anything real, it's not perfect. So when they're assembled, there are gaps between the bricks, and some aren't fully snapped together. Some are slightly smaller than other ones. Some are warped and some are skewed. And they also have slight color variations. If they're not from the same batch, they can be slightly different colored, even if it should be exactly the same. And of course, they're reflective and quite bumpy. Most of the bumpiness comes from the molding or the cooling process of the plastic. So typically the thickest part of the plastic has a peak, and where it's thinnest has sort of a dip in the surface. And because you play with them, they get scratches and fingerprints over time. So they're far from perfect, even if they are very, very well made. And then there are, of course, transparent bricks, which is a completely separate beast. You can see the inside of them. They refract light and reflect light, and they're not easy to render even with ray tracing. So there's a lot to consider when you want to render realistic Lego bricks. We haven't solved all of this yet, but let's take a look at how far we've come and what Builder's Journey look like now. So Lego Builder's Journey is a puzzle game, and everything is made from Lego, and every interaction in the game is about Lego bricks. All the scenes in the game are small dioramas. And here's a small trailer for the RTX version of the game. That's what the game looks like with ray tracing on PC. But before I get into the details, let's go over a little background info on how the game was made and our workflow in general. So the original game launched on Apple Arcade, and as that is primarily a mobile platform, it's primarily iOS and iPad. We use quite a simple rendering setup. We use a Custom renderer based on a universal render pipeline for both the Apple Arcade and the Nintendo Switch version. But it was quite obvious that we needed to do something more than just tweak shaders to get a realistic looking Lego game on PC. So for the PC version, we're using a custom version of HDRP 10.31. And NVIDIA has done a great job of adding a custom DLSS implementation. We have adjusted a few things for artistic reasons ourselves, and Unity core support helped us merge some improvements from newer versions of HDRP to get a few features working better. We'll be taking a closer look at some of the ray tracing features a little later, but first I'd like to explain a little bit about our scene and lighting setup, because that has a big impact on why we're able to use different render pipelines with the same assets at the same time. So geometry is always important in a 3D game, perhaps even more so in a Lego game. Our Lego brick database contains around 4,000 bricks. All of them are provided by Lego. We have created a few bricks ourselves, but not very many. They are based on quite old 3D models, so we've done a few things to improve them. To keep a long story short, the source models don't even have Lego logos on the studs, so we do a lot of automatic processing of the geometry to add logos, bevels, and a little surface noise. They do not contain all the details, but we don't really get close enough in the game to tell that ID numbers are missing. Note that we exaggerate the edge bevels a little because we're quite far from the bricks in the game. So to get nicer highlights on the edges, we have made them a little softer than they are in real life. We only use official Lego colors, and we've tried to match them as closely as we can to the physical colors. We have three types of materials: glossy plastic, metallic plastic, and transparent plastic. The primary, most of the bricks are made from glossy plastic, and metallic and transparent bricks are rarer in the game. We built most of the backgrounds in Lego Digital Designer, which is a free tool to construct digital Lego models. We import these in Unity and start adding gameplay logic on top of that. I'll skip over the gameplay part and continue to the next graphics-related step. Most of the game scenes are lit with a mix of artificial daylight and some fake studio lighting. It's all controlled from our daytime manager, which handles the primary light, sky, and fog settings. We also use a few fake softbox planes to get some nice reflection in the bricks. So the daytime manager controls pretty much everything related to lighting. It handles the automatic rendering and baking of reflections and light probes. And HDRP, the sky, is rendered using a custom sky module. It's all fully animatable and can update in real time. And it uses a lot of presets, so the work done per scene is typically just applying and mixing some presets to get a good look. For the extended game, we have around 70 levels, and I'm responsible for lighting most of them. So we really need a fast workflow because I also have other things to do. So it's worth noting that we're using the same settings for both HDRP and Universal Render Pipeline, except for a few things that are adjusted per renderer. So as I mentioned earlier, we do a lot of automation, and a lot of that happens when you press play in Unity. So for setting up gameplay and other things, it's really nice that everything is in a strict grid and perfectly aligned. So while we're editing the scenes, it looks very much like absolutely perfect Lego models. But a real Lego model, as we saw before, has a lot of imprecision. Bricks aren't perfectly stuck together, they're skewed, they have color variations and stuff like that. So we post-process the scene to add some realness and human touch to them. As you can see in the video, we displace the bricks a little bit, add some additional noise, discolor some of them a little bit. We also add fingerprints and scratches to give some more detail. This is done with a single tileable normal map and smoothness map that is offset and rotated randomly per brick. It might be pretty subtle, but it makes a huge difference in making it look real. At the same time, we optimize a lot of things, like removing geometry and collapsing it, and selecting the correct LOD levels for the various bricks in the scene. The process is completely automatic and takes a few seconds per scene. It can remove up to 90% of the geometry. So it's a great tool for staying flexible and still maintain good performance. So if you aren't doing the scene post-processing in Unity, I highly recommend that you give it a try. It's a powerful tool. So the key principle in our setup is that everything should be as fast to work with as possible. We don't bake anything unless we have to. We keep all data live in the editor and almost only do optimizations when you press play in Unity. We're willing to sacrifice a little bit of fidelity for a lot of flexibility in our process. We want to be able to make adjustments up until the last minute. The machine should handle all repetitive or non-creative tasks, and we should spend our time on making rather than waiting. So we try to be real time all the time, and that is one of the reasons why ray tracing is a great fit for the game. So now let's move on to high definition render pipeline. Around the start of November last year, I started experimenting with HDRP to see if we could use that to get a more realistic look for the game. At that time, I don't think the ray tracing features were available, or at least we didn't have any ray tracing hardware available. So we saw how far we could get without, with a single scene, and this is what it looked like after we rendered in HDRP. And it's looking pretty good. We got some good results, but there was some way to realism. So once we got some hardware in January this year, I could start experimenting with ray tracing. And we will take a look at the different ray tracing components that we are using in the next few slides. So here's a quick overview. We are using ray trace reflections, global illumination and ambient occlusion, shadows, transparency, and subsurface scattering are some of the effects we use that support ray tracing. First is ray traced reflections. One of the key components of rendering realistic Lego bricks is believable reflections. Now, as our game is mostly dioramas that fit on the screen and have a good viewing angle, we can get some good looking screen space reflections, but the ray traced version just adds that extra bit of realism. We get correct reflections of geometry that's facing away from the camera. We get secondary specular lighting, and we can even do multiple reflection bounces if we want to. With our mostly smooth and reflective bricks, it adds a lot. We are using 1 to 4 reflection rays per pixel, depending on the quality setting selected in game. And we've made some minor adjustments to HDRP to exclude fog from reflections for artistic reasons. There are some things to take note of when you adjust settings in HDRP. Most of the effects in HDRP have some inherent noise and has denoise options. For reflections, this can really smear out details and also introduce ghosting with fast-moving objects. So we have disabled denoising, as temporal anti-aliasing and DLSS can combat most flickering in our scenes, because we have a very narrow spread of the reflection rays and therefore a low amount of noise. So takeaways from reflections is that ray trace reflections work really well for our smooth and shiny bricks. Screen space reflections, in our case, actually work very, very well, but in most other cases, it's a lot less precise. And the denoiser can blur details if you are using ray trace reflections for smooth surfaces like ours that has very small details. So next step is ray trace global illumination and ambient occlusion. We will only talk about global illumination, as ambient occlusion is sort of the same thing, only a little bit different. As with reflections, the key benefit of using ray tracing for these over screen space effects is that we can capture stuff that's not visible from our viewpoint. The difference is a lot more subtle than with reflections, but it makes a big difference to get the correct bounce colors. And opposite of ray trace reflections, actually for global illumination, we have increased the denoiser to max settings. Otherwise, we got some high contrast noise with fast moving objects, or even slow moving objects, especially in low light scenes. So that's the opposite of for reflections. So takeaways for global illumination and ambient occlusion is that ray trace global illumination works well even with a low sample count. We only use 1 sample per pixel, or 1 ray per pixel. If we turn up denoising to maximum, that gives really good results. Screen space global illumination is a good fallback when ray tracing isn't available, but it's lower quality, and it is at least as heavy to render as the ray trace version, sometimes even more so. Baked GI is static and low resolution. We use that when you turn off real-time global illumination, but we also use it in the ray tracing passes to simplify computation. So it's important that we have baked global illumination in the scenes as well. We use light probes for that. Most of the shadows in our scene come from a single sun, which is rendered using directional light. Here I've turned off ray trace shadows and enabled cascaded shadow maps Because the scene geometry is placed quite far from the camera, cascaded shadow maps are not a great fit as we lose a lot of detail where there are no geometry. When ray tracing is disabled, we do enable contact shadows, which helps a little bit, but they have a sharp transition, and as it is a screen space effect, it produces incorrect shadows in some cases. Now, if I turn on ray trace shadows, you can see it fixes these issues and generally just looks a whole lot better. The sharp to soft penumbra is delicious, and it's able to capture the micro shadows between bricks much better than shadow map techniques. Ray trace shadows are turned on per light, and we're only using for the primary directional light. Use 1 to 4 shadow rays per pixel depending on quality setting selected in the game. And as with reflections, we actually disable denoising for shadows, as we did get some ghosting when it was turned on. And once again, temporal anti-aliasing and DLSS takes care of eliminating the noise. So as you saw in the introduction, real Lego bricks are actually quite translucent, and we are using subsurface scattering to emulate a little bit of that translucency. If I turn off subsurface scattering, it looks a lot more CG. The way the light bleeds through the thin parts with subsurface scattering turned on sells the illusion quite well. And while HDRP supports ray traced subsurface scattering, we're not using it. We're using a screen space version instead. The ray traced version should theoretically be more correct, but in our case, it needs a very high sample count per pixel to eliminate noise, and it comes with a big performance impact. So we are sticking to the non-ray traced version, which works okay for our lighting setup. Right now, we're also using the same diffusion profile for all colors, which is not exactly correct. It's definitely an area that I'd like to spend more time on looking at in the future. So ray trace transparency. Ray tracing should be a great fit for rendering transparent Lego bricks, but it has actually been the area that we've had the biggest issues with. If you forgot what transparent Lego bricks look like, here's a photo. As you can see, the interior of the bricks is clearly visible, and there are a lot of nice internal refractions and reflections that really bring it to life. So let's take a look at the transparency in HDRP. So rendering transparency with ray traced reflections doesn't give us the internal geometry that we need to make it look real. This is because the renderer does a depth prepass to support the ray traced reflections. So we only get the top surface of the Lego bricks, which is not enough to make it look realistic. If we turn off ray traced reflections, we can see the interior polygons. And if we spend time on sorting and shading them properly, that might get us halfway. But we lost those nice ray traced surface reflections, so it's not really an option worth pursuing. HDRP has a specific render mode that should help us out here, which is recursive rendering, but unfortunately it doesn't quite work for us. As you can see, we lose global illumination inside the bricks, or in the refraction through the bricks. And there are some other shading issues and some distance attenuation that has caused us issues. So we aren't using recursive rendering. Instead, it led me to think about how we could solve this in a way that also applied to non-ray traced versions. And I ended up on ray marching a signed distance field of each brick to compute refraction, as well as capturing a very simplified version of reflections from the inside of the brick. So we basically rasterize the front face of the bricks, and for every pixel that gets rendered, we ray march an SDF with up to 8 refractions to compute the color density of the transparent plastic. In addition to this, we compute a single reflection from a number of combined reflection vectors inside the brick. It's definitely not physically correct, but it does give a good illusion of the interior of the brick. On top of this, HDRP handles the top surface reflection with ray tracing enabled to really sell the effect. On a side note, the SDFs are mathematically defined per brick, and thankfully we don't have that many different transparent bricks in the game that it became a huge task to set them up. It does have some limitations to render it like this because it only simulates a single brick and internal reflections are simplified greatly, but it does look convincing enough from a distance. So that's how we render transparent bricks, and it works with both with and without ray tracing. We do use, of course, some other things in HDRP. We use other effects, as you've probably been able to tell from the videos and screenshots. The only one that makes sense to take a note of is that we use fixed exposure, because that makes lighting the scenes a lot easier than having dynamic exposure. And of course, film grain and chromatic aberration is always a discussion if you should have it or not. So we will add an option in one of the next updates to toggle it off if you don't want that. So Unity's high definition render pipeline is the first renderer I've worked with in Unity that I haven't had to alter a lot of things to get to produce the results I want. The ray tracing features, while they're still in preview in the version that we are using, have proved invaluable for our scenes. We obviously have the benefit of working with small scenes with few materials, so I don't know if it scales to more complex scenes, but for us it has mostly worked out of the box. I'm not a fan of shader graph, but with a custom function, you can get around most of the spaghetti noodling. I do hope a more code-driven shader authoring approach is coming to HDRP. And HDRP has so many settings placed in a ton of different locations that it takes a long time to figure out where everything is. But that is something that I hope is improved as well. But having access to the code base is actually really, really nice when we're trying to track down an issue, even if it's quite complex to follow the code, different code paths around. It has allowed us to adjust one or two things that didn't work exactly how we wanted it. So overall, it's been very smooth sailing, and I'm really impressed with both HDRP and ray tracing in general. Using ray tracing adds a lot of complexity, so obviously the hardware needs to work harder to render each pixel. That, of course, impacts performance. But that is where the magic of DLSS comes in. We had the good fortune to work with the great people from NVIDIA who added a custom DLSS version to LEGO Builder's Journey. And to tell you a little bit more about DLSS and the Unity implementation, here's Paul Hodgson from NVIDIA.
Hi, I'm Paul Hodgson from NVIDIA's Developer Technology team, more commonly known as DevTech. And we had an opportunity to work with Lightbrick Studios to bring DLSS to LEGO Builder's Journey on Unity. DLSS is going to be available in Unity, or is already available in Unity rather, in 2021.2 beta, and will be released in 2021.2 full later this year. Our solution for DLSS was to produce a plugin. That plugin allows us to communicate with DLSS directly, and it becomes basically like a binding between the DLL for DLSS and C#. So all of our logic is actually in C#. The DLL is just a very thin plugin just to get access to that. And then we made changes to the scriptural render pipeline that was used in this product, specifically HDRP 10.3.1. We added all the changes in there. Most of those changes were kind of fairly generic. DLSS requires that you have a lower resolution initial render, and then after it's done its upscale and increased the kind of quality, then everything is at the final resolution. We had to make no changes at all to the Unity editor or player, which says something about the flexibility of the scriptural render pipeline and the plugin support in Unity itself. Now, DLSS required us to send through certain data from Unity into DLSS. The first one being the color buffer. This is a low resolution color buffer. It's jittered, or subpixel jitter, very similar to TAA. In fact, we actually use the same parts of the scriptural render pipeline for jittering the color buffer as are used in TAA. We just increase the number of actual samples that are within that. Secondly, we need the motion vectors. Unity provides these motion vectors straightforwardly. They're unjittered, so we must notify DLSS that the color buffer is jittered, but the motion vectors are not. And then lastly, we provide the depths. The depths on Unity is slightly different on the PC than it is on other platforms, in that the depth goes from 1 being at the near plane to 0 being at the far plane. So again, DLSS has the functionality to kind of support that. Once that's all in there, then you're basically up and running. We insert the DLSS just before the post-processing step so that everything is rendered at this lower resolution. DLSS is applied, and then all their post effects are at full resolution. In terms of issues that we actually had once integrating, it's very low. I mean, most of the issues were just initial kind of implementation problems. We need to make sure that the motion vectors are the right scale, they're in the right directions, those kind of things. That kind of caught us out a little bit because Unity renders its images from bottom to top. So until the final composite in Unity, everything is basically upside down. So therefore, you have to kind of invert your kind of motion vectors for in terms of Y component, but nothing huge there. The next issue we had, again, just an implementation was that in DirectX 12, we noticed significant flickering, which wasn't present on DX11. And we narrowed that down to our use of the command buffer plugin event and data. In Unity, you transmit all your data to the render thread by either plugin events or plugin events and data. That ensures that the client and worker are fully properly synchronized, everything's in order. The only exception to that is that between Unity 2019.4 and Unity 2020.2, when you sent a plugin event and data, it would not flush any existing command lists. It was a very simple solution. All we did was we inserted a last plugin event, which would flush those command lists after all of our plugin events and data. And then we had something up and running. And for the most part, it looked great. We noticed that the quality was not quite there with the texturing. And that came down to the use of bitmaps. With DLSS, because you're rendering at a lower resolution, but then you're jittering, you're trying to imply to DLSS this extra information that's not there in a normal single frame. To do that properly, you must ensure your bitmap bias is set accordingly so that your textures for a fully reconstructed screen would have the same quality they would at the high resolution. The simple solution to that is iterate over all your textures and then you set the bitmap bias on the textures. Very simple, scriptable in C#, 5 minutes work. But it didn't work. The reason it didn't work is because in ShaderGraph, you can insert explicit samplers. Those explicit samplers, you don't have control over the bitmap bias. So in order to get it working, we simply asked Lightbrick Studios to remove those explicit samplers. They used the implicit samplers that are attached to the textures. And we got the full resolution and it looked beautiful. And that was basically all we had to do, really. There was no big issues. So again, I'd like to thank you for your time. And hope to see you again.
Thank you.